Okay. Good afternoon. My name is Whitney. I'm a hardware engineer lead from Meta. And here, me and my coworker Divasa, we're going to share with you our learning about the training cluster challenges and opportunities we see for AI hardware at-scale design. So I'm going to cover the AI at scale and also the hardware requirements, and we're going to do our case study about Meta training cluster hardware design, and then Divasa later going to share the challenges and opportunities. So AI at Meta, we have two primary AI workloads at Meta. One is ranking and recommendation, and this is widely used to our applications like ads and feed. The second primary workload, AI workload, is the content understanding, so widely used for face recognition, the key point segmentation, AR and VR, or language translation, etc. AI hardware requirements. When we talk about AI hardware requirements for AI, basically it's driven by two main things: the model complexity and also the model size. So the left plot showing here is the total compute demand, right? When we train a model, they're growing over years. So we're using petaflops per second days. As a y-axis here, you can see it's growing exponentially. And the total compute demand comes from two things. One is the model complexity, the other is the training data set. Both of them are also growing. So the right plot is showing the number of parameters, also known as model size. Over time is also, you can see it's growing, like what's the scale, right? It's growing like that. And so both of them are growing exponentially in terms of AI model complexity, also the model size. So the requirement for the AI at scale, right, for hardware design, we actually need the scalable hardware design, significantly more performant, scalable hardware design. So one thing, it worth to calling out that as you can see, the content understanding model and also the DLRM, right, the deep learning recommendation model, the requirement to the hardware is also different. As you can see, the ratio of the compute demand versus the model size, right? The content understanding versus DRM, the ratio is actually very different. So there's no one hat fits all. So what we can do is, you will see during the hardware design, in terms of the hardware resource, you will see the compute ratio, the memory, the networking requirements will be different. The bottleneck will be different. So this is going to be the case that when we have a hardware design for content understanding or for ranking, and then later Divasa going to talk more about the challenges in terms of different hardware requirement. Let's look at Meta training cluster hardware design. So back in 2019, during the OCP, at that time it's still Facebook. So Facebook actually shared the single node training node we call Zion, right? And we call it large memory uniform training platform Zion. So it has an 8-socket CPU together with 8 accelerators. This is a Zion like we announced during the OCP in 2019. So let's look at what's happening today. We just talked about the model complexity growth and also the model size growth, right? So what do we need today in terms of a training hardware platform? We are talking about total compute demand, right? We're talking about the demand about hundreds of petaflops per second days. We're gonna need to support the tens of terabyte model size. And then we are very much focused on the time to training. So all of these give us a signal, right? What do we need? We need a high performance, scalable training platform. And here is our platform, AI training cluster. So we put 2 ZionEX server node, the accelerator node, into a rack, right? And then we are connecting them together through the backend switch, like in-rack backend switch. And then we are connecting all the racks together with the cluster level switches. And then we form the AI training cluster. So depending on how many cluster level switches we're gonna use, and also depending on how many ports we have in these cluster level switches, right? We can grow this AI training cluster in a big scale. You may notice we're using ZionEX instead of Zion here. So this is the difference, right? From 2019 to today, right? This is the change in terms of the system block diagram. The original Zion design is a single node training, and it has a 8 CPU, 8 accelerator together. And then moving to ZionEX, we are making Zion more extensible. We are adding the RDMA NICs to be able to scale and then to connect to the switches, right, the backend switches, to do the training together. It worth to calling out that the backend network is actually a separate network compared with the front end. It's an isolated backend network currently based on the design. So this is the Zion hardware. From the beginning of the Zion design, we actually keep the modularity, flexibility in mind, right, when we do the design. So we designed a 2-socket module server, and then we put 2 of them together to form the 4-socket as a host. And then we're using OCP NIC and also the storage modules together, right, and put it to the expansion box, what we call the I/O box. And then we still has the OCP accelerator module, and then we have the 8 accelerator module shelf, right? Connecting all of them together, this is our ZionEX design. So tomorrow we're gonna run a deep dive into the hardware design. You can come to join us. And given that, I'm gonna hand over to Divasa to talk about the challenges and opportunities.
Thank you, Whitney. Yeah. Mic check. So Whitney talked about how we've evolved our Zion, our training platform, to meet with the times of growing AI demand. And with that, you could actually see we've made Zion more extensible, built it out as a cluster with dedicated backend. This all allows us to meet the demand that we're seeing now with AI across a diverse range of models, but it doesn't stop there, right? And this is what I wanted to call out here to kind of outline what are the challenges we continue to see and the innovation that we need continuing in this space. So to talk about this more schematically, I'm picking a particular type of models, the transformers, which have become very, very popular across all of the AI. And here's a growth trend. It's growing almost 750x over 2 years. Granted, the same growth is not going to continue. It would most probably slow down because transformers are in the early stage and they're growing very much. But nevertheless, they are going to continue to grow. And the red line below shows an indication of the representative power a system would need to continue meeting that kind of demand for these models and keeping up with the same performance. And you can clearly see, and some of it is extrapolated. It's not that it's realistic to support that kind of power. But even then, if you look at that extrapolation, this is clearly not sustainable. If we were to kind of representatively indicate that this is the system requirement for future systems as the AI models grow, the trend or that bar, the red bar here, shows what is needed. But given the constraints that we have with either systems, hardware, process, just to be looking at it more realistically, the green bar is a representation of what we can actually achieve in terms of realistic performance, even with a lot of innovations. So even with all of these innovations, there's a gap. And the best way to kind of bridge this gap, according to us, is to look at it as a holistic problem across the stack, including the software, the models, the hardware design, the memory, storage, even the data center deployment, right, and network. Omar talked about it in his keynote today. Network is a key component to that too. So we want to think about it more holistically, and that's how we believe is the only way we can actually bridge this gap and solve the problem and make it more sustainable. So going forward, I'm going to try to touch on each of these components, outline some of the challenges that we are seeing as we continue to scale with the wide range of applications, and some opportunities that we look at. By no means this is a comprehensive set. It's more of a teaser or kind of an indication of the thinking that we have, but more a call to action to the larger community here to kind of engage and so that we can jointly look at these problems and opportunities. Looking at memory, I kind of skipped over compute. Compute is very well thought about. There's GPUs, dense compute, there's a lot of solutions. But memory is another very key component. It's becoming a critical component for all AI. Although the dense compute heralded the current AI deep learning, as models grow, you saw from the slide that we have earlier, the parameter sizes are growing significantly. Because of this, the memory, not just the memory bandwidth, the memory capacity is also becoming a key component. So we are seeing models reduce in their arithmetic intensity and becoming larger. So memory is becoming a critical component to the systems. And we need both bandwidth and capacity. So looking at current kind of accelerator-based modules where we have HBM is not going to be sufficient to continue scaling. So considering alternatives where we extend and exploit the hierarchical nature of memory. Memory systems traditionally have always been kind of a pyramid where we have bandwidth, lower capacity, and kind of grow in terms of capacity and reduce in bandwidth. So this needs to be more natively thought about when we build applications and exploit them. This is the only way we can continue to kind of leverage this. And looking at memory expansion, going beyond current technologies of building it on die. Having expanders with CXL, other such technologies is another important direction which can enable or unblock some of these innovations. And when we think about memory, it's not just the compute, it's not just the bandwidth and capacity. With HBM, I'll talk about briefly in the following slides, it's also things like power, cooling are becoming important. So when we think about these memory technologies, we need to think about it holistically and address these concerns. Similarly on storage. Storage is something that's been driving AI growth. The reasons these models have been so successful or popular is that they've been able to train on humongous amounts of data. So I would see memory and compute being as important as storage, or storage being as important as memory and compute to drive this AI innovation, which essentially means we need to be able to store large amounts of data and not only store them, kind of provide this as an ingest to the models that we are training on, the platform that we're training, so that we are able to kind of ingest these models, process, and learn with them. So it becomes an important thing. And potential solutions, I mean, if we continue growing with traditional solutions, we're either going to end up paying a lot more power. There are cases, as you see here, the supporting services are almost equal or more than the power footprint of the cluster itself, which is not desirable. So there is clearly some innovation needed to bring this down, things like caching data nearby, or having dedicated fabrics for storage so that they're closer to the training elements and they don't have to sit away, which needs a fundamental rethink of how we think about distributed file systems. Today, they're more disaggregated. You have distributed file system, piping the data into the training clusters. We have to think about it more holistically, put them together, and see how we can actually continue scaling. Similarly, on network, again, this is a very important component. The scale that we look at cannot be achieved with having the support of network. And the schematic that I have here shows how, as we scale the cluster, the network becomes a key bottleneck. And as we continue to scale, it's again, we need the memory and compute, but then network starts becoming the primary bottleneck. Without unblocking on the network side, any innovation that we do on the compute and memory is not going to be realizable. So the communication overhead continues to grow. And as we continue to go to larger and larger bandwidths, another challenge that we continue to see is ensuring the utilization on these networks remain high. We're going from 100 gig to 200 gig to 400, maybe even 800. But we want to make sure we have efficient protocols and we're able to drive these endpoints so that we can achieve the same high utilization. Some of the things that we've looked at, we talked about for the training cluster, having dedicated backend for distributed training, or having something dedicated for storage. And we want to continue pushing down this direction to see how we can improve and ensure that scaling and we can continue to innovate. And lastly, all of this together, but this needs to be deployed. In our data centers, it needs to be deployed not in an isolated, singular place, but everywhere, because the services that use AI are constantly growing, and we want to have this capability that's available across all of our data centers. So whatever we build cannot be a one-off solution. It needs to conform to our data center requirements, which essentially means it needs to be deployable widely. And things like air cooling. Cooling becomes a big consideration. As we start adding this capability, compute, HBM, we're pushing the envelope in terms of TDP. Now, conventional air cooling, which allows things to be deployed widely, cannot continue. We need to think about cooling solutions which can actually enable this wider. And we did see a bunch of things. One of the things that in the expo hall which caught my eye was where we have this immersion cooling, a robot goes in, right? Things like this. We need to ensure these are not one-off solutions, but these are thought about as widely deployable across the board. I hope the examples that I gave and the challenges give you a taste of the type of things that we're running into and how we are thinking about opportunities. And I want to treat this as a call to action to the wider community here. OCP has been a vibrant community and has been key in solving some of these problems, that there is a lot of industry participation, and it's not only compute or not only memory. It needs to be across all sorts of systems, storage, interconnect, network, and even data center designs, and make sure that we can flatten the curve effectively and continue to build systems which can cater to this ever-growing requirements of applications. With this, I'd like to close, and thank you. Take questions, or yeah.
So you brought up a number of points around needing greater memory capacity and bandwidth. Do you see this as an issue of computes getting starved, and do you have a problem of getting data to the right place when you're like working on like a distributed processor, like a tensor processor, or are you talking about memory size for just kind of you need several terabytes of RAM on your traditional processor?
I think it's a combination of both, right? Let's think about it from the application side. We saw models are terabyte size. So we need to build systems that are able to house these terabytes of models. And the arithmetic intensity is lower, so they need HBM-like bandwidth. Now, the solution that we could potentially do today is to scale to 128 or so accelerators, get that aggregate bandwidth, and start the compute. But that is not the best use of the power that we have for this, right? So thinking about it more separately, I think that is what I was referring to, and that's where it comes from. So it could be a solution where we have conventional processor with a lot of memory, or kind of thinking about how to actually augment memory for these accelerators themselves.
Okay, thank you.
Another question on the network side. I'm going to assume that you're probably not assuming a lot of locality between the accelerators and how you're kind of projecting the network to sort of grow. Do you have any kind of view around that? You're sort of always assuming that through the network there's always going to be probably a multi-hop path, regardless of whether two accelerators right next to each other in the rack, or they could be on the other side of the wall possibly.
Yeah, I think that's an interesting consideration. Again, it gets driven by application, right? So we could always think about a minimum scale where we don't want or we cannot kind of tolerate this multi-hop. So we want them to be closer together. We want them to be directly connected. And that could be kind of the least count of the cluster that we design. And as we have to scale out, I think considering or expecting everything to be a single hop is not going to be sustainable, and we have to build in that hierarchy. And if you look at the plot that Whitney had in terms of the cluster, we do have the rack level switches, CTSW, and so on, right, to build in that hierarchy.
Just add to that, tomorrow actually we have a panel discussion about this topic specifically. So come to the panel, and then we're going to have some like industry experts talking about the scale of the AI hardware. Yeah. That's a interesting topic. I will also refer to tomorrow discussion, right? And so this is I guess the industry is facing these like challenges. Currently, I would say, yeah, our backend network is an isolated network right now for this generation. Yeah.
So, I mean, just to add, right? I mean, I have had the same answer in the way I was mentioning to that gentleman there. So we do need dedicated backend or dedicated network so that we actually are able to scale and provide that bandwidth and latency. But expecting that to scale to the complete large scales that we have is not sustainable. So we have to think about it as a layered or a tiered approach where we have dedicated backend at a sustainable scale, and then we kind of stitch those things together to get that larger scale, which also needs applications need to comprehend this, as well as the systems we build out, right? This is going back to the co-design, because that's the only way we can actually get to that larger scale and continue scaling.
Yeah, we've seen a lot of paper about cooling and liquid immersion and all that. I wonder, when do you think, say, liquid immersion or liquid cooling become mainstream at Meta?
Definitely.
That's a perfect question for tomorrow. We actually have our Chris Malone, going to talk about these, like some of the visions about the liquid cooling, the cold plate related, right, and versus more advanced like immersion cooling.
Okay, thank you. We'll wait for tomorrow then.
Yes, please.
You're setting it up for tomorrow.
Yeah.
Kind of piggybacking on that last question about cooling, do you think that the power density, like not being able to have enough power density for these AI accelerators is limiting primarily in just footprint, or is this a problem that's actually making it difficult to get data moving through, like either needing more memory or more network capacity because the different modules are further apart physically?
I'll try to answer. So push to liquid cooling is really about two things, right? One is really the chip itself, like the TDP of the chip itself, the power density of the chip itself. Like we have this big chip, right? And then especially we just mentioned about HBM, for example. The HBM is also one of the driven factor push to liquid cooling. It's really about the power density. It's really, really high, right? This is one of the factors. The other factor is the total, for example, per rack, how much we can cool. Right? Both of them actually push into this direction. Yeah, for the liquid cooling.
Okay, so if you have liquid cooling, you can put more of these processors in a single rack? Or is that
from
kind of the idea?
From cooling point of view.
Okay.
Yeah.
Thank you.
Yeah, thank you.